Okay, so now let us discuss why spectrogram is a special case. Well, we know already spectrogram performs convolution operation on the Wigner-Willi distribution. We have seen this equivalence in the previous lecture when we talked about positivity. We showed clearly that the kernel that is used in spectrogram with respect to equation 1, that is with respect to this definition of Cohen's class, we know that the theta there in the case of spectrogram is the Wigner-Willi of the window itself that I use in spectrogram, right. So, that is what we that is exactly what we have here, but let us reinterpret spectrogram in the context of the Cohen's class particularly. Now, what is happening here is the kernel that I have for spectrogram is the Wigner-Willi of the window, and when I look at this expression, it is clear that this kernel is solely characterized by a single window. What is the role of this kernel? It is supposed to smooth the Wigner-Willi in time and frequency, but I have a single window function which is going to influence how I smooth in time and frequency. That does not give us too much freedom. Ideally, when I want to smooth in 2 dimensions, I would like to have 2 degrees of freedom, right. One smoothing operation in time and another smoothing operation in frequency. They need not be coupled with each other. What spectrogram is doing is it is actually coupling this smoothing operation in time and frequency domain, and this coupling is facilitated by this window function. They are tied together in some sense. So, this coupled smoothing may not give us too much freedom. From that viewpoint, we can talk of a separable smoothing in Cohen's class. So, now what we are discussing is slowly the different possibilities for the smoothing kernels in Cohen's class. If I think of a separable smoothing, what I mean by separable smoothing is I would like to have 2 degrees of freedom when it comes to smoothing. I will perform some kind of averaging in the time along the time axis and another kind of averaging along the frequency axis. When I want to do that, I need to introduce a kernel which is separable because I want that property, and a general form for such separable smoothing kernels is given here. It is a product of g of tau times h of minus z. Again here tau and z are dummy variables for time and frequency. So, this g will help me smooth in time, and this big H is the Fourier transform of a smoothing window that I will use in time, but which is responsible for frequency. Because I am smoothing in frequency, I look at the Fourier transform of another window function. So, I am using 2 windows here, each window performs smoothing in the respective dimensions. Obviously, the advantage is that I have an independent control of smoothing in time and frequency, unlike in spectrogram. And you should recognize that the moment you set g of tau as delta tau, then you obtain the pseudo Wigner-Willi distribution, right, and I leave that as a simple exercise to you. Because of this, that is when I set g of tau as a Dirac, that I obtain the pseudo Wigner-Willi, right. This separable smoothing kernel, that is smoothing using the separable kernel, is known as the smooth pseudo Wigner-Willi distribution, which means now I have another degree of smoothing in which is happening in the time axis. Recall the pseudo Wigner distribution from the previous lecture told us that it is equivalent to smoothing only along the frequency axis. Now, with the help of g of tau, I am introducing smoothing in time as well, and therefore, what I have is a smooth pseudo Wigner-Willi distribution, right. And the smoothing in time is being enabled by g of tau. The smoothing in frequency is enabled by this h, big H or small h, whichever way you look. So, let us look at an example to compare the smooth pseudo Wigner-Willi with the pseudo Wigner-Willi and the spectrogram itself. On the leftmost here, we have the Wigner-Willi of the signal that we have seen earlier. We have a pair of frequencies located at 2 different time centers. The pseudo Wigner-Willi is an improvement of the Wigner-Willi, but it is not guaranteed to remove the interferences, and therefore, you will also have negative valued energy densities in the time frequency plane, and that is exactly the case here. I see in this 3-dimensional plot. Earlier we have seen 2-dimensional plots, but now for the first time we are looking at 3-dimensional plots. It gives much better display, but it is heavy on the graphics card sometimes. So, the pseudo-Wigner-Willi gives me negative valued distributions, whereas the smooth pseudo-Wigner-Willi is able to get rid of the interferences, and by Wigner's theorem we know that positivity is guaranteed, and the spectrogram is designed to give me positivity. That is the difference between smooth pseudo-Wigner-Willi and the spectrogram. In smooth pseudo-Wigner-Willi there is no explicit requirement that interferences should vanish or positivity should result, whereas in spectrogram the kernel itself is chosen in such a way, and I will give you what the kernel is in a few minutes. It is guaranteed to generate positive valued distributions. However, notice that the smooth pseudo-Wigner-Willi is able to achieve better time frequency localization or smearing than the spectrogram. It may not be so obvious from the 3-dimensional plot, so I suggest that you rerun this code and look at the 2-dimensional plots. In that respect, you should remember that the smooth pseudo-Wigner-Willi can generate negative value distributions, but if you choose wide enough G and H by some trial and error, you will be able to generate positive value distributions. Of course, that is taking you closer to spectrogram, there is no doubt about it, but there is an intermediate solution. Spectrogram is only one class of positive value distributions. Smooth pseudo can also offer another class of positive value distributions, perhaps with a better time frequency localization than what you get with spectrogram. So, this again is emphasizing a fact that we have been maintaining right from the beginning, that spectrogram and scaleogram are not the only solutions to time frequency analysis. There exists a wealth of other quadratic time frequency distributions that can do a better job than either of them. So, these are some of the remarks that we have just talked about. The main message is that the smooth pseudo-Wigner-Willi is an intermediate between the pseudo-Wigner-Willi and the spectrogram, and this is this intermediate that will give you access to a repertoire of distributions, right. Now, also the ability of smooth pseudo-Wigner-Willi to remove the interferences depends on the widths of the respective windows. And in moving from Wigner-Willi to spectrogram, we have taken out the interferences, but we have guaranteed positivity, and that is required by virtue of Wigner's theorem. So, we shall close this lecture with a quick discussion on the conditions on the weighting function, and also look at just tabulate the kernels which will give rise to well known distributions. Now, I said early on that you can translate the requirements on the distribution to the kernel, and this is exactly in line with that. If I want marginality of the module, then you can show the derivation is just of, but what is important to understand is that the kernel will determine whether the particular distribution satisfies or possesses a certain property. We shall close this lecture with a discussion of 2 points. One, on the fact that the property of the distribution, that or a desired property of the smooth Wigner-Willi is essentially equivalent to placing certain requirements, or is achieved by placing certain requirements on the kernel function f itself. And 2, we will look at a table of well known distributions that are achieved by specific choices of the kernel itself. And what you could do is look at the table, look at these requirements, and see for yourself what properties each of those distributions satisfy. So, let us quickly go through this discussion on the equivalence between the properties of the smooth Wigner-Willi and the restrictions on the kernel. The first property of interest is always marginality, but we know from Wigner's theorem the moment marginality is satisfied, then you cannot there is positivity is not guaranteed. So, to ensure that the smooth Wigner-Willi satisfies the marginality requirement, I need to have the kernel satisfy these 2 requirements, that is the value of the function at the respective axis should be unity, which means that f of nu comma 0 equals 1 and f of 0 comma s should be 1 for time and frequency marginals respectively, right. And I am not proving this for you, the proof is fairly straightforward. All you have to do is start deriving the expression for the marginal densities from Cohen's class, and then ask when is the marginality satisfied, and you will come to this requirement. For a detailed derivation, it is not too much to see because it is just about 4 or 5 lines. You can refer to Cohen's book, where the restrictions on these kernels for each of these properties is derived in detail. Now, if I want the total energy to be satisfied, that is, I integrate, I take the area under the smooth Wigner-Willi distribution in the time frequency plane, and I want that to be the energy of the signal, then the kernel should necessarily satisfy this property, that is, its value at the origin in the Doppler and delay or Doppler and shift plane should be 1. And if I want real value distributions, which Wigner-Willi does give me, then this kernel should be conjugate symmetric. And likewise, if I want time and frequency translation invariance, then the kernel should be independent of time and frequency, that is, it should be independent of tau and z. And scaling invariance requires that this kernel now should be a function of the product of nu and s, that is, wherever nu and s appear, they should always appear as a product in the kernel, and we will see Choi-Williams distribution is one of those which is scaling invariant. Recall what is scaling invariance. If I dilate or compress a signal, the same should be reflected in the energy density as well. And if I want the instantaneous frequencies to come out right, like the Wigner-Willi does, then again the kernel should satisfy these requirements. In fact, you should readily check that the Wigner-Willi satisfies, remember, for the satisfies all of this, and the kernel for the Wigner-Willi is that f is 1 at all points in nu and s. So, it satisfies the total energy, it satisfies the marginality, and it satisfies the real valued and so on, and the Wigner-Willi has all of these properties, right. Let us look at this table of some well known distributions. This is not exhaustive, but these are some of the most familiar ones. It is natural to start with Wigner-Willi, where this kernel function takes on value of 1 in the entire nu s plane or the Doppler delay plane, and the problem is it is not guaranteed to be non-negative. Why? It is obvious, because it satisfies the marginality requirement, it is not guaranteed to be positive by virtue of Wigner's theorem itself. The pseudo Wigner-Willi uses this kernel h of s. Of course, we have used h of tau earlier and h of t and so on, but remember, all of these are dummy variables. Essentially what this means is pseudo Wigner-Willi performs only smoothing in one dimension, and the smooth pseudo Wigner-Willi is a separable kernel. It actually significantly reduces the interferences. Now, recall that when we talked of smooth pseudo Wigner-Willi, you should not get confused here. The expressions are given for f, whereas if you look at the expression that we gave earlier for smooth pseudo Wigner-Willi, we gave in terms of theta, which is a 2-dimensional Fourier transform of f. There it was a product of a time window and a frequency window. Because f is the dual of theta, the kernel now is the kernel for f is a product of Fourier g of nu and then a product and the time window, right. So, it is just a dual. So, that is why you should not get confused between two expressions, they are absolutely equivalent. And then you have the familiar Rihesek distribution, which was one of the early distributions to appear contemporaneously with Wigner-Willi. This is a simple kernel, and the problem with Rihesek distribution is that it could be complex valued and could also be negative valued, but it has a certain simplicity to it. So, it is more of academic interest to look at this distribution. So, there are other distributions. Let me specifically talk about Choi-Williams, which I said earlier is scale invariant. Look at the expression for the kernel. We said if I want scale invariance, I want the nu and s to appear as a product in the kernel all the time, and it does appear, although there is only single expression, it is a Gaussian like function, Gaussian like kernel in the 2-dimensional plane, and sigma is a user defined parameter. Depending on the way you choose your sigma, you will be able to get less smearing and more smearing and so on. So, the property of this Choi-Williams distribution is also scale invariant, which is not the case with many of the other distributions, of course, apart with Wigner-Willi being an exception. Right. Then there is this Born-Jordan distribution which improves upon the Choi-Williams, where it preserves the time and frequency support. So, there are certain requirements, and many textbooks tabulate these requirements on the kernel function, very exhaustive set of properties, and you can refer to those books for a complete list of the restrictions on the kernel for properties. And you can see that the Born-Jordan distribution satisfies the requirements on the kernel, which will produce time and frequency supports. And then you have another distribution which is called Zhao-Atlas-Marx, which is a smooth Born-Jordan distribution. So, it performs an additional smoothing. Of course, the one that is of interest to us is the spectrogram, which once again tells me that spectrogram is a class of smooth Wigner-Willi. Here the kernel is nothing but the ambiguity function of the window. Well, it is a complex conjugate of the ambiguity function of the window. We have not yet studied what are ambiguity functions, and in fact, now this propels us to look at what are known as ambiguity functions. You can also specify, remember, the kernel in terms of theta, which is a dual Fourier, two-dimensional Fourier dual of f. In this case, the theta is the Wigner-Willi of the window itself. This we have seen earlier in the previous lecture, and even in this lecture we have shown that spectrogram is smooth Wigner-Willi, where the smoothing kernel or the convolving kernel is the Wigner-Willi of the window itself. And from this you should understand, even before we have defined ambiguity function, that the ambiguity function and the Wigner-Willi are two-dimensional Fourier transform duals of each other, because f and theta are, therefore ambiguity and Wigner-Willi should be two-dimensional duals, and that is exactly the case, and we will see that, we will prove that when we talk of ambiguity functions in the next lecture. To conclude the lecture, let us take a look at some of these distributions on a signal that we have seen earlier. I have 3 atoms here of 3 different frequencies. These are amplitude modulated. The middle one, the center atom, is the one that has the lowest frequency. And what I have shown here is the Wigner-Willi distribution, right, and then I have shown you the Choi-Williams on the bottom, and on the right top I have the smooth pseudo Wigner-Willi for you with a certain choice of windows. I have ensured that these choices will generate positive value distributions, and then I have the spectrogram for you on the right bottom. Obviously, Wigner-Willi gives me the best time frequency localization, that is, the energy smearing is minimal, but it generates negative value distributions. And on the other end, I have spectrogram here, which is generating positive value distributions. Of course, a smooth Wigner-Willi also does, smooth pseudo Wigner-Willi also does that for me, and the Choi-Williams also does the same job for me. And you can now pick which distribution is good for this particular signal. Right. Once again telling you that there exists a repertoire of quadratic time frequency distributions that can analyze the time varying frequency content for you. It all depends on which signal you are looking at, and what we have been studying is the math behind these distributions and what freedom I have in choosing these distributions and what properties they are guaranteed to have and they are not guaranteed to have, and so on, right. So, what I suggest as an exercise is try out the other distributions, routines for which are available in the time frequency toolbox, and see for yourself how they differ for this particular signal. You can also generate distributions for other signals as well. Good luck, and I will see you in the next lecture.